This is lesson 3.5, friction affecting the motion. So, first of all, a few things. What is the normal force? Because the normal force is actually a big part of friction. And it's really just a reactive force of a surface due to gravity. Now, if we were to talk about a level surface, we know a person standing on here has a force of gravity, however, does not actually fall through the floor. Why? Because there is a normal force acting upon it equal and opposite to gravity. Now, if this person were standing on a slope, gravity goes down this way, but the normal force goes this way, and so we can say that it is actually a perpendicular reactive force of a surface due to gravity. Now, what is friction? Friction is the reactive force that resists motion. Okay, now when we say a reactive force, what we mean is it's going opposite with another force, and it's simply reacting because something is happening, something else is happening, right? And so in the case of friction, if a car is moving to the right, this is the direction of the motion, friction would act within the opposite direction. Now, there are two types of friction. There is static and dynamic. Now, static is to get things moving, where dynamic is to keep things moving. And static is, in fact, the larger of the two. So if we were to take a look at that, the idea here is that we have an object moving, and these things are not actually perfectly level at an atomic level. Even if it's actually what we would consider ice smooth, if we took it at an atomic level, we still have these ridges. Now, there's a force being applied to the right, which means friction is moving to the left here, but if we had an object that was sitting in here as opposed to just bumping over the top, it would be a lot harder for us to move said object than just gliding over the tops of the bumps, which is why static is actually a little bit more difficult for us to actually view. More difficult for us to get things moving than to keep them moving. Now, there is a formula associated with the normal force and friction force. It is on your formula sheet. It's FF is equal to mu force normal. Now, what is the mu? Mu is the coefficient of friction. Okay, coefficient of friction. Now, this is something that happens when it basically is how bumpy are the surfaces. It has no units, and it is due to the nature of the surfaces. Because it's due to the nature of the surfaces, you're either going to be calculating the coefficient of friction, given the coefficient of friction, or in fact the coefficient of friction is completely meaningless, such as what we've done in some of our problems previously. Now, if the forces are not on a level surface, right, we would have a normal force going down. We would have a force of friction this way. Well, the net force between these two reactive forces actually would be kind of a combination of here. It's actually caused by reacting to the gravity, where the sum of these three forces creates motion down a ramp, assuming it's actually moving down said ramp.
let's talk about friction. So what I have here is a block with two masses on top. This will increase the normal force of the block. And I have here a force probe. And this force probe measures how much force it takes to pull this object. So right now, if I pull, say, with 5 newtons, and this thing's not moving, I know that the force of static friction is 5 newtons that way. Just by virtue of the fact that it's not accelerating, I know that my pulling force must be balanced with another force, and in this case, it's the frictional force between the block and the table. So what we're going to do is we're going to do a demonstration, and we're going to graph the force versus time. So let's check that out. Here I am pulling harder, 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 and then I overcome static friction, and now the block is moving. It's sliding along the table. Great, let's look at this graph a bit. So you can see right here, as I pull harder and harder and harder, the force probe is measuring the force of friction, so the force of friction is getting higher and higher and higher. The force of static friction is only as large as it needs to be to prevent motion. So I keep pulling harder and harder and harder until I reach the maximum. See the tip of that peak, that's the maximum value of static friction, and then the block starts moving. And this is all kinetic friction. Notice that the kinetic frictional force is smaller than the static frictional force. That's always the case. Let's go to the whiteboard and take a look at this. So here's the graph that we just made by pulling that ball. So as we discussed on the computer, this is the maximum static friction force. And the force of static friction, well, it's equal to μs times the normal force. That is, the maximum is equal to μs. In general, force of static friction is less than or equal to the coefficient of static friction times the normal force. And this coefficient of static friction, it can be 1.2, it can be 0.8, it can be 0.4. It depends on the material. It depends on this guy's surface and this guy's surface. That's what it depends on, this surface and this surface. And, you know, if you were to zoom in to try to see what's going on, okay, let's zoom in a million times. Well, here's the table. It looks smooth, but it's not smooth. And here's the block. It looks smooth, but it's not smooth. And so you see that these bumps and stuff, it's like teeth. They have to go against each other. And that's what you're overcoming when you pull hard enough and it starts moving. And all along here, that's the kinetic frictional force. And the kinetic frictional...
I will just say that instead of kinetic friction, we called it dynamic friction. Basically, it's friction while things are moving.
The force is equal to mu k times the normal force. And that's the force of friction while the object is moving. So since they both have normal force here, we can divine that the coefficient of static friction is greater than the coefficient of kinetic friction. This is by...
Okay. So what do parallel and perpendicular forces act on an incline? Well, first of all, what do we mean by parallel and perpendicular? We've got an object on an inclined plane, and it has a force due to gravity acting upon it. Now, if we call our set of axes kind of along the plane, rather than a normal vertical, horizontal, XY, what we can see is we can actually break gravity up into two pieces, where this force runs parallel to the surface, and this force runs perpendicular to the surface. Now, the perpendicular part of gravity should be equal to and opposite the normal force. So the force perpendicular goes against the normal force. And this is because the object actually does not fall into or leap off of the surface, that these things would in fact be equal and opposite. Now, the force parallel will run against friction, assuming it's sliding down. Now, if it's sliding up, again, it will be combined with friction. It's harder to move things up, but it runs with or against friction. Because friction, the motion would be parallel. And so if we wind up with a situation where this is on an inclined plane, what we do is we actually treat the motion and we kind of tilt our axes into a perpendicular and a parallel axis rather than using the traditional X and Y. Let's take a look at a couple of examples here. So we've got a 10 kilogram chair resting on a horizontal surface of a desk after being thrown by Allison. What's the normal force asking on the chair? Well, this chair, it's just sitting here. It's got a force of gravity which will be equal to the normal force because the chair is just sitting there. So the force of gravity is going to be equal to 10 times 9.81, which means it's equal to 98.1 newtons, which means the normal force is going to be equal to 98.1 newtons. Now, this is down, and this is up. Now, Devin tilts the desk to an angle of 33 degrees. What's the normal force asking on the chair now? Well, if this is 33 degrees, we know this is 98.1. We've got here and here a parallel and a perpendicular component. This angle would also, in fact, be equal to 33 degrees. And that's key because these are running parallel and perpendicular. It's a 90-degree angle. We've got the hypotenuse and the angle, and we want to find the adjacent. So we use cosine of the angle is equal to adjacent over hypotenuse. So the 33 degrees, we're looking for the adjacent. The hypotenuse is 98.1 because that's what gravity is. So 98.1 cosine 33, make sure your calculator is in degree mode. I'm going to make sure my calculator is in degree mode. And we'll just type in cos 33, and that gets you a value of 82.3 newtons to 3 digits. Or 82 newtons if you're going to 2. Now, if the coefficient of friction between the chair and the desk is 0.2, so we know mu is equal to 0.20. What is the frictional force against the sliding motion of the chair? Well, we already know that this chair has a, and I know this is not great to scale, we know the gravity, we know that this normal force is 82.3 newtons. We've got the coefficient of friction, so the force of friction is equal to mu force normal. So we're really just taking this and multiplying it by 0.2. Now I'm keeping my calculator answer even though I wrote 82.3. We're just multiplying by 0.2. Gets you 16.45 or 16.5 newtons to 3 significant digits. Now, as an aside, we could calculate that parallel force and see if this would actually slide down or whatnot. Let's just do that for fun. I know this is not part of the question, but if we were to take the 98.1 sine 33, the amount of force that is causing this thing to slide down is actually 55.4 newtons. So we got 55.4 newtons this way, and only 16.5 newtons opposing motion, which means this actually accelerates and falls down and hits the floor. It hit Brett's on the foot. Brett is upset, and he pushes this along the horizontal surface with a coefficient of friction at 0.28 being the coefficient of friction. Because the surfaces have changed, the coefficient has changed. But because we're now on the level surface, the force of gravity being 98.1 and this being 98.1 means that the force of friction is equal to mu force normal, or 0.28 times 98.1, which gets you a force of 27.5 newtons. And again, we're not really surprised. Well, the surfaces have changed, as well as the fact that it's going to be a little bit more solid. It should be expected we'd see more friction. To keep it in constant motion, how much force does Brett need to apply? Well, to keep it in constant motion, the net force has to be 0. The force of friction, the force applied, the force of gravity, and the normal force. Now, the normal force and the gravity, they cancel themselves out. That's not a problem. The force of friction, we know, is 27.5 newtons, which means to keep it in constant motion, we're going to need to apply an equal and opposite amount, 27.5 newtons. Now, if he applied 75 newtons of friction on the floor, what is the acceleration? Well, that net force acting upon it is going to be that 75 that he applies minus the 27.5 of friction. So that gets you a total of 47.5 newtons of net force. Well, we know that F is equal to ma, or A is equal to F over m as written on our formula sheet. So we're going to take that 47.5 divided by the 10 newtons. That gets you 4.75 meters per second squared as the acceleration. Now he notices that it's about to hit him. It's accelerating towards him at 4.75 meters per second squared. He's got a distance of 5.0 meters away. We know it started from rest. We're told that in the problem. How much time does Ben have in order to answer the question, to move out of the way? Well, fact is that really Ben should just move out of the way and not actually calculate this, because otherwise he's going to get hurt. But Ben decides to do the calculation anyway. Well, we know that d is equal to VIT plus 1/2 AT squared. Now the initial velocity being 0 means that this is all 0, and 0 plus anything is itself. So 5 is equal to 1/2 the acceleration being 4.75 t squared, multiplying both sides by 2, right, to get rid of the 1/2. We're going to take 10 divided by 4.75 to get 2.10 is equal to t squared. And then we're going to have to square root. It's 1.45 seconds that he has. Unfortunately for Ben, is that when he noticed, it took him more than 1.45 seconds before he got hit by the chair.
Forces on an incline is an essential component of any introductory physics class, and you've got to take it. Here's how. This forces on an incline plane apparatus will turn the pencil and paper approach into a hands-on experience. Each module comes with a built-in scale. Use this to measure the normal force. And there's a protractor which helps you measure the angle as the weight decreases with the cosine of inclination. But at the same time, the force component downhill increases with tilt. That's the sine component. Now for an example. I have here 500 grams, which weighs 5 newtons, and I'm going to tilt to an angle of 37 degrees. And now the force downhill is 3 newtons, and the normal force is 4 newtons. But of course it is. It's the famous 3-4-5 triangle, and each component is a leg of that triangle. What about 45 degrees? 3.5 and 3.5 newtons. And 3.5 squared plus 3.5 squared is 25. The square root of that is 5 again. It appears that the forces always add up like the legs of a right triangle, and the hypotenuse is the weight. The weight, which is the largest force, is broken into 2 component legs by the physics of the incline. But now, with the forces on an incline plane apparatus, this diagram becomes usable data in your hands. And there are many activities that you can do with this device too. For example, you can graph specific relationships, you can verify specific predictions, and more than anything else, you can gain an intuition for these subtle concepts, making forces on an incline much more easy to understand and a lot more fun. This works.
Okay, because Ben failed to move out of the way in time, he's required to answer the following questions. Poor Ben. Okay, 225 Newton trunk is being pushed up a 25 incline with a force of 197 newtons, so the trunk is moving up the incline with a constant velocity. Okay, so let's think about what's happening here. We've got the trunk, it's got force down of 225. It's being pushed up with 197 newtons, and the net force here is got to be balanced. So what's the gravitational force running parallel to this? Well, that parallel component of that angle, which we know is 25 degrees, is just going to be 225 sine 25, because it's a right angle. Again, making sure your calculator is in degree mode. So that's the parallel component. The perpendicular component is going to be 225 cos 25. That gets you 204 newtons. What are the sum of all the forces acting on the trunk? Well, that's got to be 0. Why do we know that? Because it's a constant velocity. So what is the size and direction of the frictional force? Well, we know that this has a weight of 225. Its perpendicular component being 204. It means that the force normal is 204. So the normal force is 204. We're applying with 197 newtons this way, and we know that it is 95 newtons this way, which means that there is an overall force of 102 newtons that we have to account for. Where is that coming from? Well, that's going to be coming from the friction. If all these forces canceling out, it's moving up the ramp, so friction is moving down the ramp, opposing the motion. These two forces need to add up to this one in order for everything to be equal to 0. So what is the coefficient of friction? Well, we know that the force of friction is mu times the force normal, or we can say the force friction divided by the force normal is equal to mu. So 102 divided by 204, that gets you 0.5 as being the coefficient of friction between the surfaces. I think I just answered E here, where this is D. 102 down the ramp. Yeah, that's D. That's E. My apologies. Okay, taking a look at example 9. Well, what happens if the net force is not 0? Well, we've got a one for 14,000 Newton car. It's parked on a 32-degree slope. The one causing it to go down the hill, that's the parallel force. Being at a right angle, we know the force down is 14,000. Means that we take the 14,000, and this is the opposite over hypotenuse, so it's sine 32 degrees. That gets you 7,418 newtons. The normal force on the car, well, it's not sinking into or off the ramp, so it's going to be equal and opposite to this perpendicular component of gravity. So that's 14,000 cos 32, which gets you 11,872 newtons. So what is the acceleration of the car if the brakes fail and there's 3,000 newtons of frictional force? Well, let's think about that. Here we've got this car. We know it's got 7,418 newtons tending to go down the hill. And so we've got 3,000 newtons holding it up, which means that the net force total, we know it's the net force because the perpendicular and the normal force, say, are equal and opposite, is going to be 3,418 newtons. To find the acceleration, we go A is equal to F over M, and mass. We don't have mass, we have weight. Well, fortunately, that weight is just equal to MA, which is 9.81, so we can find the mass by simply dividing the weight by 9.81. So we're doing this to find that the mass is 1,427 kilograms. So the acceleration is going to be that net force of 3,418 divided by the mass of 1,427. So that gets you an overall acceleration of 40 meters per second squared if we're keeping it to 3 significant digits. Last example here. What is the acceleration of a 30 kilogram object with a 22.5 degree incline with a coefficient of 0.3 between the object and the incline? So it is a 30 kilogram object, which means the weight, force due to gravity being equal to mg, that weight is 30 times 9.81, or 294.3 newtons. We can find the parallel and perpendicular components to this. And we know it's 22.5, 294.3 sine 22.5. And so we'll do these calculations. This one is 112.6 newtons. And the other one is 271.9 newtons. Okay, this being proportional, equal, and opposite to normal force means that to find the normal force, it's just going to be equal to 271.9 newtons. To find the frictional force, well, that's going to be equal to mu force normal, or 0.3 multiplied by 271.9, which gets you 85.6 newtons. So we know the frictional force holding it up. The force tending to go down is 112.6. Friction is holding it back, 85.6. So if we were to take an 85.6 and a 112.6 and figure out the difference between the two, that should get you a net force of 31 newtons. Well, it's a 30 kilogram object. Net force of 31. A is equal to F over M. So we take 31 divided by 30 gets you 1.03 meters per second squared. And that's going to go down the ramp. Okay, if you do have any questions, please let me know. Otherwise, thanks for watching.